Good morning, students. Today we are going to discuss about the Zener diode, a special semiconductor device, Zener diode. In the first class, we discussed about the Zener diode. Overview, we discussed about the Zener diode. What is the working principle? Introduction of the Zener diode. Characteristics of the Zener diode. So what are the different applications of the Zener diode we discussed in the previous class. So now we try to discuss about elaborately about the Zener diode formation, Zener diode breakdowns, and comparison with the other devices, and also with the comparison with the two types of breakdowns, advantages and applications of the Zener diode in this class. So now first we try to discuss about the difference between the PN junction and Zener diode. So already you know that the Zener diode is nothing but a PN junction diode, but it having the heavy doped diode and it is operated in the reverse bias without damaging the device, without breaking the device. So now we try to discuss what are the main differences, how it differs from the PN junction diode. Difference between PN junction and Zener diode. The major difference between PN junction and the Zener diode is that the PN junction diode allows current to pass only in the forward direction, whereas the Zener diode allows the current to flow both in the forward and reverse direction. So this is a general difference. We can simply say that. So the PN junction diode is the unidirectional device. It can flows the current, it can allows the current in a one direction, that is in the forward direction. Coming to the Zener diode, so Zener diode in the forward bias, it is also act as a PN junction diode, that is it allows the current in the forward bias. In the reverse bias also, it allows the current. Why? Because if you applying the more and more reverse bias voltage at the junction, what happens? Due to the avalanche breakdown or due to the avalanche breakdown or due to the Zener breakdown, more number of charge carriers are generated at the junction. So because of this free charge carriers, it allows the current through the reverse bias also. So that's why PN junction diode allows current to pass only in the forward direction, but the Zener diode allows the current to flow both in the forward and reverse direction. The next, the PN junction diode used for rectifier purpose. The Zener diode is used as a voltage regulator. The PN junction diode is used for rectification purpose. What is the meaning of rectification? The alternating current or alternating energy source is converted into the DC source, AC to DC conversion. AC, for converting the AC to DC, we use the PN junction diode. That is the best application of the PN junction diode. Coming to the Zener diode is used as a voltage regulator. Voltage regulator means if you apply any fluctuated or any type of voltage to the Zener diode, the output of the Zener diode is a fixed, a constant voltage that is offered by the Zener breakdown of that particular Zener diode. So that is the difference of the PN junction diode and Zener diode. The PN junction diode is used for rectification purpose. The Zener diode is used as a voltage regulator. So now we try to discuss elaborately about these differences between the Zener diode and the PN junction diode. The key differences between PN junction and Zener diode. The following are the key differences between the PN junction and Zener diode. So we try to discuss some of the differences between the PN junction diode and the Zener diode. We know the semiconductor which conducts only in one direction is known as the PN junction diode. The device which can conduct in one direction is called as a PN junction diode, that is forward bias. You already know the operation of the PN junction diode. Whenever we apply the forward bias, what happens? The positive is forces the holes to overcome that depletion layer. The negative terminal oppositely forces the electrons to overcome the junction barrier. Once it reaches the forward voltage 0.3 or 0.7 depending on that material, it crosses the junction, the current will be flows exponentially, the current will be flows increasingly. So that is the operation of PN junction diode. The semiconductor device which conducts only in one direction is known as the PN junction diode. PN junction diode. And the Zener diode is the silicon diode which is optimized to operate in the breakdown region. So Zener diode also made up of with the silicon material, silicon and germanium only, silicon material. So what we are doing is we make that diode should be optimized to operate in the breakdown region. The reverse current flow through the diode damages the PN junction diode. What do you say? The reverse current flow through the diode damages the PN junction diode. So the meaning is, if you in ordinary PN junction diode in the reverse bias, if you apply more reverse bias voltage to that ordinary PN junction diode, what happens? It damages the depletion layer, it damages the PN junction diode, and that damage causes the short circuit. Ultimately the device may burn. And the reverse current due to this heavy electrical field which we are applied at the junction, for the reverse current flow through the diode damages the PN junction diode. It itself burns itself. The junction burns itself. Burning means completely ashes out the devices. The reverse current flows through the diode when it is connected in reverse bias. Coming to the Zener diode, the reverse current through the diode when it is connected in reverse bias, the reverse current will be flows here. It does not damages the device. If you decreases, the reverse current will be goes to 0 and the diode will be at the same position. So that is the difference between the PN junction and the Zener diode. The reverse biasing means the p-type material is connected to the negative terminal of the supply and the n-type material is connected to the positive terminal of the supply. As we already know, the reverse biasing means p-type is connected with the negative terminal and negative n-type is connected with the positive terminal of the supply. So that is called as a reverse bias, as we already discussed in the PN junction diode operation. But the Zener diode allows the current to pass through both the direction. What happens? The Zener diode allows the current to pass through both the direction. Zener diode current passing is appeared in the both the biases, forward bias and the reverse bias. The doping level of the PN junction is low as compared to the Zener diode. So the PN junction diode, ordinary PN junction diode, doping is low. Why? Because the Zener diode is nothing but a modification of the PN junction diode. After inventing the PN junction diode, so what they thought that how we can use this reverse bias. So how we can use this reverse bias condition of the Zener diode. So by that thought, they do the experiment on this reverse bias. By doing the experiments, finally they achieved a phenomena called breakdown without damaging the device. Without damaging the device, they find the breakdown, and the feature of that breakdown is the voltage is constant. Whatever the voltage you are applying, the device at the particular Zener voltage, and remaining the energy is converted into the current. So that is the Zener breakdown. So that's why the Zener breakdown Zener breakdown doping level is of the PN junction diode is low as compared to the Zener diode. Zener doping level is high. So that only we are getting the reverse biased current without damaging. The width of the depletion region depends on the doping level. If the doping level of the diode is high, the depletion layer region is low, vice versa. So you know that the width of the depletion region, already you know depletion layer is formed at the junction. At the junction, depletion region is formed there. Why? Because the free charge carriers are recombined across the junction. At the junction, what happens? The ions become the more positive, negative ions become the more negative. So that what happens? At the junction, we don't have any free charge carriers. If doping level is low, the depletion layer width is increases. If doping level is high, the width of the depletion layer is decreases. So that's why he's saying that the width of the depletion layer depends on their doping level. Depending on the doping level, if the doping level of the diode is higher, doping level of the diode is high, their depletion layer region is low, and vice versa. The depletion region is low. So if the depletion layer is low, what happens? If you apply the negative voltage or reverse bias, more reverse bias, what happens? Fastly the electrons are comes from the what is say stationary ions by breaking its covalent bonds. So they freeze the free electrons. The covalent bonds of this stationary ions may damaged when the bond is when the band is when the bond is breaks. What happens? The bonded electrons and holes are get freed and come to the conduction band. So like that, if the depletion layer is low, we can get the more number of free electrons in the reverse bias with applying the small amount of reverse bias voltage. The breakdown in PN junction diode occurs at high voltage level, whereas in PN junction diode it occurs at low voltage levels. That is, the meaning is the breakdown in PN junction diode. PN junction diode is occurs high voltage levels. Why? Because it is the damaging process. If you apply the more and more reverse bias to the ordinary PN junction, what it do? It goes into the damage mode. It go try to damage the device. So for damaging the device, we need the high voltage levels. But whereas in not this is a PN junction diode, whereas it is in Zener diode, it occurs at low voltage levels. That is, the voltage levels we can vary. Why? Because we only deciding the Zener breakdown voltage at the manufacturing. We try to manufacture the Zener diode such that we need to get the particular PN junction diode. The breakdown that is what you said. The Zener breakdown at the lower voltage level. At the manufacturing, we can say that the doping level, what amount of doping we use for particular what amount of Zener breakdown. If you wanted to get the some sort of Zener breakdown voltage, we need to optimize the doping and concentration of the actual PN junction diode. So like that, we have the different range of Zener diodes are there. But coming to the PN junction diode, it does not have any range. It having the generally it having the 0.3 0.7 forward voltage is there, and it acts as a just like a switch. So to increase that current capacity, increase its stability, and for that we may increase that material, but the operation is as same as we can discussed. But in the Zener diode, each diode have its own Zener breakdown is there. The Zener breakdowns are different compared to the PN junction diode. PN junction is a general purpose on and off device, but Zener diode is a special purpose, specially for specific Zener voltages. We will get the Zener diode. For particular Zener voltage, we need to have a separate Zener diode only. Not we can convert a one Zener diode having the higher voltage into the smaller voltage. It is not possible. It's not possible. That is the difference of the Zener diode. That's why it is called the special semiconductor diode. These are preferred for specifically for the specific purpose only, specific application only. We are using the Zener diode. The breakdown is the phenomena of making the depletion region conductive. What is this breakdown phenomena? Breakdown phenomena is nothing but whatever the depletion layer is there, making that depletion layer into the conductive, depletion region into the conductive by generating the free electrons, either Avalanche breakdown or with the Zener breakdown, whatever it may be. You may use Avalanche breakdown or Zener breakdown, but what the purpose, ultimate purpose is to making the depletion region into conductive region. The heavily doped diode has a low depletion region. As we already know, the heavily doped diode has a low depletion region. The PN junction obey the Ohm's law. What you say? The PN junction obeys the Ohm's law. What Ohm's law says? The current passing through the conductor is proportional to the applied voltage. Whatever the current is passing through the conductor, that current is proportional to the applied voltage V proportional to I. So the PN junction diode obeys the Ohm's law, means if you increases the voltage, automatically current also increases. Current also increases, very proportional to the current. But coming to the Zener diode does not obey the Ohm's law. Why? Because in the PN junction in the forward bias, just like a conductor, it is a short circuit. We can neglect the 0.3, 0.7, a small voltage drop across the PN junction diode. Irrespective of this small voltages, it is acting as a short circuit. Short circuit is nothing but a conducting wire. So conducting wire is always follows the Ohm's law. Voltage is proportional to the current. But coming to the Zener diode also voltage increases, current also increases, but not proportionately. Some sort of voltage is dropped constantly across the Zener diode. Some sort of voltage, by depending on that breakdown voltage indication, that amount of voltage must drop at the Zener diode. So remaining voltage only converted into the current. Remaining voltage only flows in terms of the current. So that's why the Zener diode does not follow the Ohm's law. This is the main difference between them. The Ohm's law said that the voltage applies across the diode is equal to the product of the current and resistance applied across the diode. In technical terms, you can say like this. The Ohm's law says that what it's saying, the voltage applied across the diode, the voltage applied across the diode is equal to the product of the current and resistance applied across the diode. That is nothing but a V equals to R into I. The diode resistance and current will give the applied voltage. So that is the meaning. The PN junction diode obeys the Ohm's law, whereas Zener diode not obeys the Ohm's law. The PN junction diode is mainly used for rectification purpose, whereas the Zener diode used for providing the constant voltage to the load whose voltage is varying. So what is doing here? PN junction already we mentioned. Generally it is used for the rectifier purpose. Rectifier means converting the AC to DC. The AC signal is converted into the DC signal. Alternating signal is converted into the direct signal. The Zener diode is used for providing the constant voltage to the load. Constant voltage to the load where the supply voltage is varying. In the varying conditions, by using the Zener diode, we can give the a constant voltage to the load. So this is the advantage of the Zener diode. So Zener diode may also used as a switch in the forward bias, But the application, specific application of this Zener diode is voltage regulator. Voltage regulator, it regulates the voltage. So now we try to discuss another differences between the PN junction diode and Zener diode. So now we try to compare. So what are the as we are discussed those things. Now we try to discuss in the form of the chart, in the tabular form. You can see how it is. You can see this is for the simple understanding, and for the exam purpose you can simply write these points. In the last we discussed elaborately about what is the differences and why are the differences are there. We give in the explanation. This is simply we can give the chart form and see how it is. The comparison terms, on what terms we are comparing PN junction diode, Zener diode. First we try to discuss a simple definition. PN junction diode. PN junction diode is a semiconductor diode which conducts only in one direction, that is in forward direction. Simply can say PN junction diode means it is a semiconductor diode which conducts only in one direction, that is in forward direction. That is the PN junction diode definition. Coming to the Zener diode, the diode which allows the current to flow in both the directions. It is a device which allows the current to flow in both the direction, that is forward and reverse. Such type of diode is known as the Zener diode. Simple way you can say that the Zener diode will allows the or flows the current in both directions. Both directions. You can see the symbol. The diode symbol is just like Zener, also same like as the diode symbol, but the indicating line, that is a cathode anode line, that line shows the which one is positive, which one is negative. Before the line is positive, after that vertical line is the negative. Same way this Zener diode, that line is replaced with the Z, that is a simple Z. Same way before this Z is placed, after that is the minus, that is they indicate the terminals, positive terminal and negative terminal of the Zener diode and PN junction diode. That what is say the plus and minus is very important, because the device of PN junction diode, if you connect in the reverse bias or in the forward reverse bias, it does not flow the current. So that is the important thing we need to remember. I can say reverse current effect. How it is, how the reverse current effect. If the reverse current flow to the PN junction, then what happens? It damages the junction. The overall the device will be damaged. Damages the junction. Coming to the Zener diode, it do not damage the junction. In the Zener diode, the reverse current effect does not have, the only passes the current through the junction. Doping level, how it is? In the PN junction diode, doping level is low. In the Zener diode, it is high. Breakdown, how it is occurs. The breakdowns in the PN junction diode in higher voltages, but in the Zener diode it is in the lower voltages. Ohm's law, PN junction diode will obeys the Ohm's law, but Zener diode does not obeys the Ohm's law. Application. The PN junction diode is used for the rectification purpose, and the Zener diode is used for voltage stabilizer, motor protection, and wave shaping. Motor protection also we are using the Zener diode. We say meter protection, but motor protection it is. So these are the some of the simple differences between the PN junction diode and the Zener diode. Okay, so until we discussed about the differences between the PN junction diode and Zener diode. This is the broad discussion about these differences. Now we try to discuss about the further differences of the Zener diode. That is a main basic phenomena of the Zener breakdown and the Avalanche breakdown, which are the basic things happen in the Zener diode. So the first one is the Avalanche breakdown. So what is the Avalanche breakdown? We try to once briefly discuss and then we compare in the short form. The mechanism of Avalanche breakdown occurs because of the reverse saturation current. The p-type and n-type materials together forms the p-n junction. The depletion region develops at the junction where the p and n-type materials are contact. As we already know, the mechanism of Avalanche breakdown occurs because of the reverse saturation current. If the reverse saturation current generates in the device, this Avalanche breakdown will be developed. The p-type and n-type materials together, we can already know PN junction diode will be formed when we clubbed p-type material and n-type material. The depletion region develops where it will be develops the depletion region. The depletion region develops at the junction where the p and n-type materials are contact, where these are contact together. At that contact the junction will be developed. The p and n type materials of the PN junction are not perfect. Why? Because p type is not pure holes it having, n type not it have pure electrons. The p having the more number of positive charge carriers, a considerable small amount of negative charge carriers also there. Coming to the n type also we having the large number of negative free charge carriers, that is electrons, but also it has small number of positive charge carriers, that is the holes, are called as the minority charge carriers. That's why the p type and n type materials of the PN junctions are not perfect and they have some impurities in it. That is, the p type material has some electrons and the n type material has some holes in it. The width of the depletion region is varies. So because of this, what happens? The depletion layer region at the junction is varying because these charge carriers may recombine at the junction. Their width depends on the bias applied to the terminals of the PN junction, P and N region. The width of the depletion region depends on the bias applied to the terminals of the P and N region. The reverse bias increases, the electrical field across the depletion region increases. What happens? The reverse bias increases, the electrical field across the depletion region also increases. When the high electrical field exists across the depletion region, the velocity of minority charge carriers crossing the depletion region increases. what happens? The velocity of the minority charge carriers crossing the depletion region is increases. Whatever the minority charge carriers are there, because of this reverse biasing, they move towards the p type material. Whenever these minority charge carriers crossing the depletion region, because of this high electrical field, the velocity of these minority charge carriers are increases. The velocity of these minority charge carriers are increases while crossing the depletion region. So these high velocity carriers are collide with the atoms of the crystal, which they are situated both sides of the depletion region. These high velocity carriers collides with the atoms of the crystal. So because of this violent collision, high speed collision, a strong collision, the charge carriers takes out the electrons from the atom. Whatever the minority charge carriers are there, they take out the some more electrons from the atom, the collision increases the electron hole pair. This violent collision, this high speed velocity minority charge carriers violent collision increases the electron hole pair. As the electron hole induces in the high electric field, they are quickly separated and collide with the other atoms of the crystal. So because of this high electric field, these generated electron and holes are separated fastly, and they also acquire the that electric field and get the violent velocity, and then they takes the other electrons from the crystal. That is, the as the electron hole induces in the high electric field, they are quickly separated and collide with the other atoms of the crystal. The process is continuous. What happens? Again, after induced or after developed electron hole pairs, again they collide with the other atoms and they generate the more and more electron hole pairs. The process is continuous. And the electric field becomes so much higher than the reverse current starts flowing in the PN junction. What happens? The process is continuous and the electric field becomes so much higher than the reverse current starts flowing in the PN junction diode. This process is known as the avalanche breakdown. After the breakdown, the junction cannot regain its original position because the diode is completely burnt off. So this process is known as the avalanche breakdown. After the breakdown, the junction cannot regain its original position because of the diode is completely burned out. So this is occurred in a normal PN junction diode, that is called as a avalanche breakdown. So now we try to discuss about the Zener breakdown. You know already Zener breakdown. The PN junction is formed by the combination of the P-type and the N-type semiconductor material, as we already known. The PN junction is formed by the combination of the P-type and the N-type semiconductor material. The combination of the P-type and N-type regions creates the depletion region. The width of the depletion region depends on the doping of the P and N-type semiconductor material. If the material is heavily doped, the width of the depletion region becomes the very thin. The width of the depletion region becomes the very thin. So what is the meaning? If the material is heavily doped, the width of the depletion region becomes very thin. The phenomena of the Zener breakdown occurs in the very thin depletion region. So where we are getting this breakdown, Zener breakdown is in the very thin depletion region. Very thin depletion region. The thin depletion region has more number of free electrons. The thin depletion region has the more number of free electrons because of the heavily doping. The reverse bias applies across the PN junction, develops the electric field intensity across the depletion region. The reverse bias applies across the PN junction, develops the electric field intensity across the depletion region. The strength of the electric field intensity becomes very high. The strength of the electric field intensity becomes the very high. The electric field intensity increases the kinetic energy of the free charge carriers. The electric field intensity increases the kinetic energy of the free charge carriers. Thereby the carrier starts jumping from one region to another region. These are the minority charge carriers. So because of the heavy doping, we having the more number of free charge carriers in the reverse bias. Because of the electric field intensity increases the kinetic energy of these free charge carriers. Thereby the carrier starts jumping from one region to the another region. Those energetic charge carriers collide with the atoms of the p-type and n-type material and produces the electron hole phase. The reverse current starts flowing in the junction, because of which depletion region becomes entirely vanishes. This process is known as the Zener breakdown. So generally this Zener breakdown is says that because of thin depletion region and more ions are depleted at the depletion layer. So what happened means, at the time of junction formation, what happened means at the time of junction formation, if the p-type material and n-type materials are heavily doped, p-type materials and n-type materials are heavily doped, what happens? Heavily charged carriers are recombined at the junction. If heavily recombines, what happens? At the p side we having the more number of positive ions, more concentrated positive ions, and n-type we having the more number of minus negative ions, more concentrated negative ions are there. If you applied more and more reverse bias, what happens? These concentrated ions are energized, and some of the covalent bonds of these ions may break. These the covalent bonds are break there. When the covalent bonds are breaks, what happens? Number of free number of electrons hole pairs are generated. If you increases more and more reverse bias voltage, what happens? More and more covalent bonds are breaked in the depletion region. More and more electron hole pairs are generated across the depletion layer. Like this, more number of free charge carriers are generated in the depletion layer. Hence, the depletion layer is makes the conductive. So then the electrons are flowing through depletion depletion region. Once this breakdown is occurred, this type of breakdown is called as a Zener breakdown, which is occurred in the heavily doped PN junction diodes. Once this Zener breakdowns occurs, whatever the reverse bias you are applying, that reverse bias is converted into the intensity of the electron flow, but it does not change the breakdown voltage. Once it is entered into the conductive mode, there is no drop across the Zener diode, only with having the only Zener voltage drop. So this is about the Zener breakdown, elaborately about the Avalanche breakdown and Zener breakdown. In the next class, we try to discuss about the difference between the Zener breakdown and Avalanche breakdown. Thank you.